Perfect. Thank you so much. All right, so for a high-level overview, the talk is kind of split into two parts. There's going to be a really short part where I'll be talking at a high level about methodology for porting to OpenACC with OpenMP as a sort of a stepping stone. And the longer portion, I'll try to jump into these case studies in some more detail, where for each of the case studies, I'll talk about the code a little bit. I don't want to focus too much on the actual science. I kind of want to talk more about the porting process. And then I'll talk about the OpenMP, OpenACC porting of the loop. And here I really want to stress that what this talk is going to be about is about expressing the underlying algorithmic parallelism. So we've heard before how you can use OpenACC or OpenMP to slap some directives in front of loops and get some additional performance from it. However, I want to really stress that you don't want to limit yourself by the existing parallelism of your code. You don't want to limit yourself by the existing implementation. What you really want to do is modify the code that you have to expose more of the parallelism that's there in the algorithm, right? Not in the particular implementation that you're dealing with. And then for each of the case studies, I'll also talk a little bit about optimizing the data motion. I'll show a call tree and where the data motion takes place. And then finally, some performance results for each of these case studies. So the first step, and again at a really simplified high level, is to port to OpenMP. And I really think that this should be done first before you port to OpenMP. The primary reason, I think, is because most of the scoping work that you do when you port to OpenMP can be reused when you're porting to OpenACC. So, things that are scoped private remain so. Things that are scoped first private remain so. And I think most importantly, things that are scoped shared in OpenMP are really highlighted as things that are going to require data motion potentially for OpenACC. So if you do this porting process to port your code to OpenMP on the CPU first, then when you follow up later to do your OpenACC port, I think you'll find that a lot of the work has already been done, and there's sort of some fine-tuning that will remain. And so sort of as the first step, you can slap on some directives to express the existing loop-level parallelism with your current implementation. And then some loops and some codes maybe need to be modified a bit, like I say, to get more of the underlying algorithm's parallelism. And this perhaps won't be as much of a problem with OpenMP as we'll see, but this becomes even more important with the OpenACC porting. So with respect to OpenACC, I think it's really important to look at the loop trip counts or the iteration counts of the loops. You may find that some loops that had enough parallelism for 1632 cores perhaps don't have enough parallelism for the hundreds or thousands of threads that are going to be necessary on the GPU. So one great way to make sure that the loops that you're considering are actually good candidates is to use something like Cray, because it will highlight that loop iteration count for you. And then you can go ahead and start adding some OpenACC directives. And I think the point that I'd like to make here is that I find it's a lot better to do the OpenACC kernel creation and the OpenACC kernel optimization before you deal too much with data motion. I mean, sure, if you have 2, 3, 4 loops next to each other that reuse some of the same data, it's sort of a no-brainer to wrap a data region around that in the beginning. Absolutely. Especially because as you're working with this code and doing sort of the iterative development cycle that happens in code development, this can speed up your development if you're not waiting on the data motion. So, it's something that you can do if it's easy as you go. However, if you don't really know what kernels are going to perform well, you don't really know what kernels you're going to use, it's kind of hard to perform a good data motion optimization. I think what I like to say is that you really want to have known data requirements before you spend a whole lot of time worrying about data motion optimization. So that's why I say what you really should do is optimize the device host data motion last, and I recommend a bottom-up hierarchical process for that, which I'll talk a little bit more about in detail when I show the call trees associated with each of the 3 case studies. So with that, I'd really like to go ahead and jump in to these case studies. The first one is TACOMA from General Electric. It comes from GE's Brian Mitchell. And I mean, again, I'm not going to say too much about the science here other than, well, it's a CFD code, and we'll move on. So we're going to look at an example loop nest here, and this loop is loop nest is representative of a number of costly loop nests, a number of costly routines. So if you look at the profile, tackling this particular shape or style of loop nest can then be applied throughout the code. So you can get a lot of reuse here. So this was made to parallelize on the CPUs with OpenMP fairly successfully. And once we jump into that, I think you'll see why that doesn't work so well for the GPUs and what needs to be done to sort of solve that problem. So we'll look at the original loop structure. This is simplified, but really the idea is that we're computing this df, this deflux. It's 3 values. And then we're going to apply this deflux, this df, to this result array R. So we'll add the values to some positions and subtract from some other positions. And so what you see here is that if you were to run each of these iterations in parallel, you have this race condition because multiple iterations could be storing to the same IJK location. And really to highlight that in red, I'm showing these -1. So really you can think of this -1 offset as being the issue. So with OpenMP, we went with a coloring scheme. So the idea is that each thread gets a color. Certain portions of this result array R are also assigned a color. And before you write to or modify the R array, you just check it first to see if it matches your color. And because of this offset, you may have to change your loop bounds just a little bit. That's sort of what this light color of orange or blue represents. But this is how this might look like in code. So again, the idea is you just check this my color. It could be a function or pre-computed as an array or something. And you just make sure that the cell that you're modifying belongs to you before you write to it. Now, as you saw with the coloring picture, you kind of have a little bit of extra work associated with each of these threads. So when you move to this sort of a solution and you move over to the GPU, instead of having 16 threads, each one with a tiny bit of extra computation, if you were to use this sort of an approach on the GPU, it won't really vectorize. Each thread would require the additional work. And so there's too much additional work to be done. So we had to come up with a new approach to get this to work with OpenACC. And so what we did in this particular case was, I guess I'd call it a loop fissure and index translation. So we split the loop. First, we compute all of the deflux values. And then once we have the deflux values pre-computed, we can make the observation that a -1 on the left-hand side is +1 on the right-hand side. So now that we have the +1 values pre-computed, we just use them. And then you notice the stores to R are all to the independent IJKs. And so this will parallelize and vectorize beautifully. Now, it's true that there's a little bit of additional memory use and perhaps a little bit of additional memory motion on the GPU itself. However, this turned out to be a pretty good win in a number of cases. One might point out that there's perhaps some corner cases to deal with, and the beautiful thing with this particular problem was that I guess you would say that the halo, the surface cells of this particular result array aren't used anyways, and those are the corner cases. So if those aren't computed correctly, we don't care. So this turned out to work very well for us. The data motion for this turned out to be a big problem. We came up with a pretty good optimization in the sense that you can see we start at the leaves, and there'll be, I guess I'll focus on data region V perhaps, the second data region from the left on the bottom, and you can see that there'll be some data motion into the beginning of the data region. You can see that with an orange arrow. Then that data can be reused throughout the life of those 3 kernels, and then perhaps some results transferred back by that other orange arrow. But you can see that you can build these data regions hierarchically so that you can kind of divide and conquer, and you don't really have to look at all of the kernels at the same time. You can start to group them into their own data regions. But really what kind of killed us here is that you have a time step with data motion in and out, and then you have communication. And in this particular case, we weren't quite able to move everything over to the GPU, and so this data motion became a bit of a problem. So we still came out with a win, I would say, for weak scaling, and this particular graph highlights some of the problems with small scaling. And in particular, you can see on the bottom left that those 2 data points would have, say, 200,000 cells per CPU core. But as you move over to 64 nodes as opposed to 4 nodes, you only have 12,000 cells per CPU core. And this isn't enough work to keep this running efficiently. And you can see that at that point, we actually have lower performance than the CPU only. Now, I could probably make a different graph with a bigger problem to tell a pretty picture. But I mean, I think this is an important thing to highlight, that these GPUs seem to work really, really well for weak scaling and sometimes have some problems with strong scaling. The second case study is Delta 5D. It's a fusion code from ORNL's Donald Spong, and I apologize, I won't really talk about the Boozer space particle orbits. It's the science, and I'm just kind of focusing on the porting effort. So for this code, there's a loop. It's a single loop. And I'm going to cheat a little bit and just say that when we ran this with OpenMP, this loop didn't take a very long runtime. So we just ran it in serial. It wasn't a problem. But once you move this to the GPU, you find out that it runs too slow in serial on the GPU. And at first thought, you might say, well, no problem. We'll run it on the CPU where it's fast, but this would require data motion to the host to run on the CPU, and then data motion back to the GPU once you're done, and the data motion makes this, it's too prohibitive. So we need to parallelize it. So really what this calculation is doing is we're just going through a list of particles, checking to see if this particle has escaped a particular confined plasma volume and appending it to a list of escaped particles. So it's a simple append operation. So this is sort of the first version of the code, slightly simplified, but things look very similar to this. And you can see really the problem is with this I loss equals I loss plus 1. There can be a race condition there if these iterations are all run in parallel. So the solution here for version 2 is just to use atomics. And I think this was a really neat case that had a real-world code that had this come out with a really large win. I'll show performance in the next slide of that. And the other nice thing about this particular code is it really only required data motion in at the very beginning, and then data motion of results out at the very end. And there really wasn't a time step communication in between. I guess you could say this is ideally or embarrassingly parallel in the sense that at the end of the computation, there's a little bit of coordination, but during the computation itself, there isn't a lot. So the data motion was greatly reduced in that sense. So Again, I think the point I'm trying to make here isn't so much that this came out with a giant win for this particular code, but that it took a computation that should have been a small portion of the runtime and brought it back to the state where it takes a small portion of the runtime. So this particular kernel was 45 times faster, and for the total runtime, like I say, depending on the parameters, we can knock 5 to 10% off the total runtime. Again, taking something that really should have been, almost no time at all back to about no time at all. So it was a good solution for us in that code. And the code that I want to spend most of the time talking about is this final code, NekCEM. This was a code that I got introduced with at the ORNL hackathon. The hackathons are a lot of fun, by the way. I think someone else mentioned those. Gosh, I think I put in 14-hour days every day, but it was a whole lot of fun. I recommend them to everyone. So again, I'm not going to go too much into the code details themselves there. I mean, the science details, we'll jump right into the code. So this particular loop does not vectorize on the GPU at all, and we'll talk about why. The other point I'd like to make here is that we really want this to run on the GPU kind of for two reasons. First of all, it's performing a gather-scatter, and we'd really like to take advantage of the high bandwidth available on the GPU. And second of all, currently you do a gather-scatter, then there'll be some MPI communication, and then there'll be some more gather-scatter. So if we were to put these gather-scatter operations on the GPU and leave the MPI communication on the CPU, we'd have this data motion problem all over again. So what we really wanted to do was be sure that these gather-scatter kernels, as well as the MPI communication, all took place off the GPU. So we're using, I guess you could either call it GPU direct or CUDA-aware MPI, so the MPI will come directly out of the GPU memory without touching the host. So I guess I'll talk a little bit about this. This is just one of the scatter operations, and the idea is that the data is coming from this bottom array U, and this description vector, I guess you could call it send map, is telling the scatter where to put the data from U. So for one particular example, we'll look at this first one. So there's this 3, and that says go to 0, 1, 2, 3. There's the 1. And then the next two elements before the -1 says to put that in the destination buffer in position 0. Hey, there's our 1. And in position 1, there's our 1. And then that ends. Then we have another vector that describes another transfer to do, and so on. So this is really a vector of vectors. And this could be laid out in a different way, but this is the way that the data structures were laid out with the code that we have. And so I really wanted to make, the minimal changes in order to optimize this. So we stuck with this data structure. So version 0, I'm not even going to show because it has a whole bunch of, goodness, it's like a 6 to 8 level deep call tree with C preprocessor macros. And so when you condense all of that and inline it, you get this, which looks really messy because we have a nice mix of while loops, do while loops. There's a bunch of pointer arithmetic. So this sort of stuff doesn't vectorize well at all either. Moving to version 2, I was able to condense this down to a nice triple loop nest. However, you still see those -1s there. So the issue with this is that these loops don't terminate until they hit a -1 in this vector of vectors. And the compiler doesn't know this in advance before the loop starts, so this cannot be vectorized. But what's nice is that this particular section was packing and unpacking some things to communicate with neighbors, and the neighbors that you communicate with are the same throughout the lifetime of the computation. And so the sizes of these things can be pre-computed. And so you see here in version 3, we pre-compute all of those sizes, again, as opposed to re-architecting the entire code. That would be a lot more work. And then we get this beautiful triple loop nest that we can vectorize and parallelize without issue. Here you don't see any orange arrows, because there is no longer any data motion at all. Everything takes place on the GPU, including the MPI communication. And you can see gather, scatter, kernel, communication, gather. It's all on the GPU. And so for this particular code, I want to start with I think this is pretty impressive. We come up with the same result by using 39% of the energy of the CPU run. So, it would be tempting to say the power used is less by the amount of time that's reduced, but it pulls a little bit more power while it's running. So, just to get that exactly right, we went ahead and did a real run there. And then finally, for the overall performance of this code, we did really well. This was about a factor of 3. And you can see that we got it to the point where now we can do the entire computation, this red dot, in a tiny bit more time than it took to do just the gather, scatter, and communication portion before. And you see this uptick here in the scaling as the MPI communication starts to become an issue. And you don't have that as much with our communication on the GPU because we have 1/16 the number of MPI ranks, because we have 1 rank per node as opposed to the 16 ranks per node. And also that CPU rank isn't doing much. It's all the GPU. So again, I just want to kind of stress the key points that I'm trying to make here. First of all, OpenMP porting to the CPU is really a great stepping stone. You can reuse a lot of the scoping work, and frankly, it's easier. So if you can do something easier that's a stepping stone to something harder, go ahead and do it. I would recommend optimizing the data motion last. And sort of what I tried to show with those call trees is that you can perform this bottom-up hierarchical data optimization process, again, to kind of do a divide and conquer, so you don't have to look at all of the kernels and all of the functions at the same time. And finally, the number one key point that I think I've made with all of these examples is that, in this day and age, you can't get away with just slapping directives in front of existing loops and expect to get good performance. You really need to modify the loops themselves to be sure that you're expressing the algorithm's parallelism and not the parallelism of the code you started with, because the code you started with probably doesn't express enough. And here's the legal slide. Any questions?